Okay, everyone, I'd like to thank you for your time here. Before anything else, I'd like to acknowledge my collaborators for the AutoML research, Akihiro, Rado, Pari, and Elizabeth, and for the Lale and Julia collaborators, Martin, Kiran, and Abraham. The outline of my talk is just 1, 2, 3, 4, and if you have enough time, I can discuss more about the use cases. But let me start with the introduction of Julia, HPC and Julia, and then Julia in data science with R and Python and Lale, and then some use cases. So before anything else, let's have a quick look of what's the development of programming languages in for the past years. So if you can still recall, IBM in the 1950s introduced Fortran and specifically for high performance computing. And then you have this list with this symbolic programming environment for especially for AI. And then you have the C, which is now 50 years old. Fortran is 71 years old. I'm trying to emphasize the age of these programming languages, which are still we are using. And then came S and R 45 years ago, MATLAB, C++. And then I think in the 1990s, you have these interpreters like Ruby, Python, and Perl, and then you have this Java programming language also. And then recently you have 9 years old, 9 years ago, Rust and Julia. So if you look at the development of these programming languages, it seems that we are stuck somewhere in the I think in the 2000s or 1990s. And then we are just having a new programming language recently. So basically in a typical programming, the idea is just to translate the high-level language into from human language into the low level for machines, and there are different ways to do that. So you have the interpreter, which is the advantage is that you have high interactivity, real-time translation, but you have this REPL that does this interpretation to the machine. If you have the loop, this REPL becomes very slow. So you have highly interactive system, but very slow in terms of performance. And then you have at the extreme side is the compiler. It will read all the codes, make it into a machine code so that when you have a loop, then there's no more interpretation. It will just run directly to the machine. And then you have this middle ground where you have a bytecode interpreter so that you can have more machines running in different architecture. So you have a bytecode interpreter that can, like a middle layer that translate from the bytecodes into the machine. And then recently, with the advancement of compiler design using LLVM, you have this just-in-time or sometimes ahead-of-time compilation. An example of this is Julia, Lua. I think Swift is somehow ahead of time also. And some of these other languages also are trying to adapt to this. So the idea is that you have a very interactive kind of interface, but at the same time, the codes are compiled just in time. So I give you an example of the differences of this to make it easy. So I create here a random numbers of 100 million. So I'll not run this in the interest of time. And then I created a Julia function, which is basically to sum these numbers. And it took me, let me run this. So if you time this, hopefully my CPU is not taken over by the WebEx. It runs like 3.5 seconds, 16 bytes, and so on. This is the answer. And then if you're using C, I can embed C actually in Julia. So this is actual C. And then I embed it with the C code, and then I can compile it using the libdl, and then create a Julia interface to call the csum function, which I compiled, and pass this data structure, the types, like this is an array of types, and it should return a floating value. And then if I time that, let's run this. It took me only 0.2 seconds, the same value, the same result, right? So both of them are compilers, so it should be fast. What about interpreters like R? I can embed R using rcall with this thing. So anything that is inside the triple quote with R, this is what we call it R interpolation, is the real R function. So it still sum the value. If we sum it, it took us 2.3 seconds versus 0.2 seconds versus, sorry, this is not, there's a compilation delay there. So the thing in Julia is that there's a pre-compilation, so you have to run it a second times to really measure the speed. So after the compilation, it's 0.3 seconds. And then if you have Python, you can also use py-call in Julia to embed any Python functions inside using the py what we call the string. So any inside this triple quote is a Python code. I can run it and then measure. It took me 10 seconds to do that. So if you're going to implement things in a real in the programming language per se, then you have this kind of speed differences. But if you're going to call the numpy sum or the sum libraries in Python or in R, there's not much difference because they are written in basically in C code. So calling them should not make any difference. The only difference is that if you're going to implement these loops in the language in the languages that they implement. Now, in the reason why Julia is fast is because it basically create a machine code. So if I sum this is this is the low level code. This is the machine code. It immediately runs and compiles. So it is a compiler. So it's not much different from C, and you have the interactivity at the same time. So let me have a brief look of the Julia history. It started with 2009, but they announced it in 2014. So for the past, I think 7 years, they tried to stabilize it. And so 2018, the Julia conference was in UK. I was there. And then they basically announced this. And I would like to mention that in 2017, IBM sponsored the PowerPC port. And right now, in the 2021, there are now 29 million plus downloads, 203,000 GitHub stars, and 6,000 packages, which is very, very fast right now. I think in daily, you have so many packages that are being registered. So it runs in Windows, Linux, OS, FreeBSD, and ARM, which is in Android, in your iPhone, Intel, in PowerPC hardwares also. So it runs basically in all the popular platform. For the benchmark, let me just show you, because this is the favorite thing that we would like to show. So these are the different kind of problems: matrix multiplications, Fibonacci, quicksort, Mandelbrot. And these are the speed. The lower the value is the fastest. C is a baseline. Julia is here. Lua Giante is here because this is just in time. Rust is here. Go is a little bit slower. Fortran is here. Java, as you go to the right, you have the interpreters, and the speed will be slower. And then Octave is the slowest. And I'd like also to say that JuliaCon is in next week. There's right now a workshop, this is free. So the workshop right now is running is GPU programming in Julia. So you can basically program directly in GPU using the high-level language in Julia. These are other topics: quantum computing, mathematical things, game development, simulating big models, package development. These are all free. So please feel free to register and attend some of the sessions. All of these are all recorded in YouTube channel of Julia, so you can also watch them. And then I would like to mention also Julia, these are the links, and these are the case studies. Pharmaceutical modeling, like your COVID, is using differential equations, and they use a lot of Julia. Space planning, financial modeling, a good example is that, parallel computation in astronomy. Julia is developed in MIT, so a lot of these people working in high performance computing are using Julia, and even they replace MATLAB for their high performance computing lectures in MIT and Stanford and many others. Okay, please read all of this, and if you have problems in Julia, you can go to Julia Discourse, and these are the topics in Julia. So you will see it's all scientific and mathematical programming, probabilistic, aerospace, finance, optimization, medicine, healthcare, Julia at scale, and so on. So these are very busy discussion group, and you can join and ask if you are interested for more information about Julia. And I would like also to plug my GitHub. I'm maintaining 3 or 4 packages in Julia: the Lale AutoML pipeline, pipeline in R. And there's a Julia workshop that I created, which is a binder. When you click this, the binder will create it's like an OpenShift virtual machine, and will run. You can run the notebook here. I will not wait for this thing to spin up, because this is a Docker image that is run in a virtual machine, and it will take some time. Okay, let me go now to the heart or the matter. So let me give you an example of the main features of Julia, and then I will give you some use case, distributed computing Julia, and so on. So Julia is a multi-dispatch. What do we mean by multi-dispatch? It dispatches based on types. So it dispatches, for example, if it receives 2 integers as argument, it will dispatch like this. If it has received integer and float, it will dispatch with this. So that means to say that you can have different behaviors depending on type. So if I say F12, this is integer, so it will dispatch. I will dispatch. This is the dispatch. If and then I can ask which function did you dispatch? Yeah, I'm using this signature. If I do this, it will dispatch the integer and float. And then if you're lazy, you can basically create just a x and y. You don't have to say the type, because Julia is doing type inference also, and it can specialize on this type inference. You can also create a restriction, like if my function is only processing float, I can say x and y is float, such that t is a subset of float. Then it will dispatch, right? And then I have so many definitions of f. I can have now a collection of f. This is what we call multi-dispatch, because you have f, but it dispatches to different signatures. So a good example is the methods of class. It dispatches with so many different customized, like linear algebra, matrices, so many. You can add more dispatches. If you customize your code, you create a new custom data set or data structure, and then add dispatch for your class. And then when you see your code, you don't see functions, but you see operators, which is much easier to understand instead of having these functions. So just-in-time compilation. What is just-in-time? So when I created the Julia function like this, at this point in time, Julia does not do anything because it doesn't know whether x is an integer, is a float. But when I call this thing, then it will create what do you call this? A native code specific to integer. So I will call LLVM because it's much easier to say. You will see here 6 is an integer, so I created an integer native code. If I make it a float, it will create a double float. So that's where high performance come in, because it will create a data type specific to the memory model that you need. So if just imagine if this is an array of integers or array of float, this will be very, very efficient because it will just create big enough size for your memory. Now I give you another power thing idea about type Julia. You can create a parametric types in Julia with this kind of syntax. I want my x and y to be a t, where t is a real number. So this is what do you call this? This is a customized type. Now I can create a point which is a float type. If I do this 0, 0, my point is an integer, so it will create a integer type float. So again, this is a very important in efficiency, because your data structure is using the kind of data type that you need. So it will create a, what do you call this, infer what kind of arguments you want, and then it will create a specific type for you. So now I can create two points. And then I can create an operator between points. Like, for example, if I want points A and B to be added, I can just say, I can overload the time. Let's just say multiplication. Let me say it's plus to make it easy. And then I will change this to plus. So for example, I want an operation for my customized data type, and say I want to add 2 points, right? So I can just overload my dispatch, and then I can now add point A plus point B. See? So 3 plus 1, 4 plus 2, and so on. So I think by this kind of example, you will now see that in Julia, the technique is usually you create your data structure, you create your operators, and then you do your programming by just what do you call this, combining operators, which I think somehow tells you this is very similar to mathematical kind of programming, because you will see a lot of operations similar to your mathematical operations. Now let me now show you an example of how to interface Julia with R in Python. So rcall for calling R, Python for py call, and then I can embed Python here, and then I can run, for example, I can pass the data set which is outside of Julia, which is a a vector of random 10 numbers and call Python in the background. Yeah. And then I can also use np-sign, which is a numpy. I import numpy here, so I can call np-sign and then pass the data outside. This is outside. There's a serialization involved, but py call will do that for you. Or you can import py as np and then use np-sign random. So this is now really looks like a real Julia language programming, because you don't see any Python code anymore. You can, for example, use py plot, which uses the py call and make it as a package. So this py plot actually calls Python in the background, and you can plot your things similar to what you're doing with Python. And then with scikit-learn, I can import the ensemble random forest classifier, and then I can import the data set using py import, which is part of our call, and then load the data, fit, and predict, and look at the accuracy, and you can have this. So there's not really problem in calling R and Python inside Julia. In R, I can run ggplot, for example. I can load ggplot and plot the iris dataset and so on. So there's really no issue where if you are in Python world and in our world, because Julia is very friendly with these two programming languages, and even C or Fortran. You can call them immediately. Okay. So let me shift now because I am running out of time. So let me show you distributed demo. In Julia, it's common to have distributed computing approach. So I have here 1, 2, 3, 4, 5, 6, 7, 8 processors. So right now I add processor. I check if it is 1, and then if it's not, then it will add the processor. Now I have 8 workers, and then I have 9 processors, including the main dispatcher. I can spawn a function to one of these. So I place it to the second worker, the random function, and then I can fetch the result. Yeah, I can spawn randomly, even if I did not specify the ID. It will just find which worker is not working, and then place the data there, and then I can fetch it. So with this idea, you can basically now do certain kind of parallelization. You'll notice here the data structure is featured because sometimes the program will run and the result will be in the future. So you don't get the data until the program finishes. So let's say, for example, you have an array of futures, and then I run the program. I spawn a very simple problem like I times I to all of these futures, and I loop them 10 times. Then I have an array of futures that are supposedly running, and then I can map the fetch function to each of them to get all the data set, and then basically I can reduce it like with plus. So this is an example of map reduce, right? I can basically do that here. So this is array comprehension. I spawn a task and I loop over n. So if I do that, I have this future, and then I will dot fetch. The dot here means that fetch element by element. We call it broadcasting. So let me do that. Then I have the result, and then all the result that is fetches, I can sum it. Easy peasy, right? I can do that much easier with this program. I add distributed, concatenate everything, concatenate the value of this. So anything that is inside is spawned to a worker, and then create 10 workers. So I have 10 workers doing the squaring, and then my result is now a vector, and then I sum them or get the sum, which is the same here. I can also create here plus, so that I don't even have to do the sum here. This is the reduction here. So I can just do that. So just imagine now you can do a lot of this distributed computing in a very, very short amount of coding, right? I can do also channels. So for example, if I have tasks, I can have a producer that create a channel, and I have a consumer. So channel, I can get the task, so take task and so on. So I can actually look over this task and spawn inside again, spawn a process to do the task. So you have a producer consumer doing this task. And yeah, it's the same thing. You can have a channel to do these things. You can have also multi-threading in Julia, like threading, number of threads right now is 4. I can have now one CPU has 4 threads, but I can have, because I have 8 workers, and each worker has 4 threads, I have now 32 threads, right? Because each work, so this is an example of having distributed computing together with multi-threading. So multi-threading, they share memory. Distributed computing, they don't share memory. So each process, each worker is separate. So you don't have to deal with it. So now it is up to your imagination how to create your application so that you can leverage with the threading in multi-Julia and distributed computing. And the distributed computing, by the way, is not only in your computer. If you have a cluster computer, Julia automatically distribute the load to your other clusters. So let me show you right now. My Julia is running like this. Some of these are workers, some of these are dispatcher. But yeah, this is local, but it is trivial for Julia to send this across different processors using either Unix socket, SSH protocol, or HTTP protocol, and many other protocol. It supports a lot of this. And then let me now give you a use case with Lale. Lale is a Python language, is a Python package which is running in, which is basically the heart of Auto AI. So we ported it recently. So basically we use py-call behind it. But if you look at it right now, I can create, so this is like Lale operators, PCA, blah, blah, blah. And I can create the Lale syntax like this. With a technique of multi-dispatch. These are operators that I overloaded. And then you can have a LAN pipeline. You can run optimizer and feed it. This is hyper optimization because it has to determine whether logistic regression is better than random forest classifier. So you can run this and you can check the accuracy, right? And then you can have classification regression. The same thing. You can have your data, your grammar here, which is like choose between PCA and no op, and then pipe it to linear regression or random forest regressor, and then do a hyper optimization of this, and then give me the result, right? And then that's it. It took us only like 3 days to port Lale. Of course, the what do you call this? The debugging took some time, maybe another week, but basically the porting was very trivial. Let me show you also the distributed approach. Like I have here workers of 8. I can run Lale inside here. This is Lale with the distributed computation of Julia. Then I can have several workers running Lale optimization inside. It's not trivial to do this in Python, but this is trivial in Julia. Look at my workers. It's running all the time, all of them, and these are the different workers running, and then I can get the result. Yeah. So the latest Lale code actually implements this visualization, but this is not released Lale because Lale is a product. The Python Lale is a product, but we have support now the visualization, and this is Julia Lale. So whatever is the result of the hyper optimization, it tells you what is the final pipeline and so on. So we plan in the future to extend Lale. It's a good leverage of Lale in Python with the Julia distributed computing. And then let me show you my program also. I am doing AutoML pipeline, which is basically similar to Lale, but I'm doing this from a different approach. So I'm doing pipeline factory, and this factory creates a lot of these pipelines. Yeah, so these are different pipelines. And because these pipelines are independent, I can run my pipeline looping over all these different pipelines and run them in parallel with all the different workers. So just imagine if I have like hundreds workers, this will be very fast. And then I can sort the final result and see which pipeline is the best. So here, for example, for this data set, normalization with PCA and random forest is the fastest. Okay, so let me go next. Is the distributed array. Distributed array is a very nice idea because if you create a typical data, the data is owned by one process only. So if I ask who owns this process, it's only process 1. But if I distribute this data and ask again, so this is now distributed array. If I ask again who owns this data, this is owned by different processes. What I can do with this is that this can be in a different machine remotely. And what I can do is I can do MapReduce. Like I ask the local part, I spawn for over all the available workers. I asked them to get the local part of that data. And then, for example, if the problem is, what do you call this, sum of the of the X squared, you just sum your local part using that worker that owns it and spawn them. So let's see what is the result. So you have array of future because every worker is doing their own part, the slice of the data, and then you fetch the result, and then after fetching it, you reduce it into sum. So this is a very example of Hadoop in Julia or Spark in Julia. You have a combination of map, fetch, reduce in very straightforward manner. And if you run this in a typical sum function, even with Julia that is very fast, oh, it seems that sum is very fast. No, it's 0.3 here. Sum is only 1 second. Of course, the map reduce is faster than sum. Although if you look at it, uh, actually sum in Julia is using MapReduce because when it sees that this data is a distributed array, it will use the reduce dimension thing. So it's doing a lot of reduction also, but it cannot beat the hand manual way of reduction. This is 0.3 seconds, this is 1 second. And then I'd like to show you something about COVID because COVID is a big thing. So I ran RCall, I ran Python at Julia and load the data here of the COVID, and then this is an example of subsetting or getting subsets of the data in Python. In R, you can also do filtering. Not much different, the same. I can filter some certain countries, Asia. I can do exploration, and then I can basically plot them using ggplot. So I create a function in Julia, but actually inside it is an R. And then I can plot, for example, Philippines. What's happening in Philippines? This is positive cases. These are the death. It's not really good. United Kingdom, there's a increase in positive cases, but flat because of the vaccination, I would suppose. And then you have Ireland. It's quite flat because we are still not opening. We are opening on July 26th. If you look Israel, it's good. If you look India, this is 400,000 spike, but and these are the death is about 6,000. But luckily, right now it's down. The scary part is Thailand. It's going up, and Indonesia is also scary because in Indonesia, this is now 40,000 positive cases and at least 1,000 death every day, and it's not going down. And Malaysia and so on. So I think that's a nice use case to show. Now, for the value proposition about the future of Julia, let me show you the future of Julia. And I hope that I was able to convince you. So Julia blurs the line between ordinary users, developers, and data scientists because you have the compiler, you can develop immediately, you can make your code available immediately. Julia packaging is so easy. We were able to, for example, package the Python libraries in 3 days and less maybe. It increase your productivity in brain cycle because things that are fast, interactivity is fast, and then the result is fast, then your brain cycle is fast. And then fast development time, fast runtime, fast exploratory time, and then promote reproducibility because you don't need to program in C anymore. You can just write in all your workflow in Julia and easy to understand. By this, I end my presentation. Thank you.
Thank you, Paulito.